In this video, I'm going to go over the process to convert files from fcheck to WFX extension to be run in the ChargeMold program. This video was made using version 3.8 of MultiWFN, so it is possible for many options numbers to change in the future. Please pay careful attention to the number options rather than the numbers. Constructing a WFX file is necessary because the ChargeMold program uses natural orbitals to calculate different properties. As shown in the equation here, the density of spin-up electrons can be expanded in terms of spin-up orbitals phi, and their occupation numbers fi. These spin-up natural orbitals diagonalize the spin-up first-order density matrix. An analogous set of equations holds for the spin-down orbitals and spin-down occupation numbers to get the density of spin-down electrons. These natural orbitals and their occupation numbers are stored in a WFX file. After reading the WFX file, ChargeMold computes density-dependent properties such as net atomic charges, atomic spin moments, and bond orders. ChargeMold can also perform orbital-dependent analysis to compute the SPDFU populations and the bond order components. The type of quantum chemistry calculation performed determines which options are available for creating orbitals. For density functional theory, DFT calculations, the first-order density matrix is already diagonal, so the natural orbitals are already stored in the fcheck file, and you have the option to just convert the fcheck to WFX directly without manipulating it. Alternatively, if you want to create a compact chemical representation of the system at hand, you can localize the orbitals. When correlated wave functions methods are used, we want to diagonalize the density matrix to get the natural orbitals and their fractional occupancies that ChargeMold needs. This video includes several examples of fcheck to WFX conversion using MultiWFN software. Examples 1 and 2 cover orbital localization for DFT calculations, while example 3 is a direct conversion of fcheck to WFX for the DFT calculation. Examples 4 and 5 cover diagonalization of the density matrix for correlated wave functions methods. A separate video will cover WFX file generation using Gaussian software. Example 1 is a DFT spin non-polarized fcheck file turned into WFX after localizing its orbitals. Open MultiWFN and the folder where you have the fcheck files. In this case, I will start with a molybdenum complex example. I chose to inspect the fcheck file and look for the word density. In this case, only SCF density matrix was found. Drag the fcheck file to MultiWFN and press enter. Options are going to appear. Select Show Molecular Structure and View Orbitals option. If you wish to have a visual representation, a window is going to open. In there, you can play with the view by clicking left, down, right. You can also zoom in and out as you wish. And you can also reset the view. Also, the axis can be turned on and off, as well as the labels. On the Orbitals box, you can choose an orbital and a representation of it appears on the window. For better visualization, you can choose the isosurface of the orbitals. The options include solid mesh, mesh, points, solid phase and mesh, and transparent phase, among others. Adjust the view for an optimal capture of the feature you want to show, and save the picture. Hit return, and the window is going to close. Now, you may notice that the image was not saved on the folder where the example is. Instead, all pictures are saved to the folder where the MultiWFN is in your local computer. So we go there and cut the picture to paste it into the directory where we are working. Next, we select the option to get the orbital localization analysis, in this case, 19. A secondary menu appears, and the negative numbers represent the orbital localization settings that we are using. Note that the localization method is the Piping-Messy with molecule population as indicated in -6 option. Choose option 1 to only localize occupied orbitals and let it run. When it is done, a new menu is going to appear. Now that the orbitals have been localized, we can visualize them by, again, choosing the option to show the orbitals. We now look that the orbitals have been localized as we now look at the orbital number 36, which was the one we took a picture of before the localization. Now, it is clear that orbitals have been localized. Save picture and click return. To save the file, choose option to show other functions, 100, followed by the option to export various files, 2, and then choose the output current wave function as .wfx file, option 4. You can choose where to save it by choosing a path for the output. For that, you can go to the directory where you are keeping the example and right-click to view properties and copy the path to paste it in MultiWFN, followed by a backslash and the name of the file. Here, we add _multi_WFN to know where the file was generated. Lastly, add .wfx to the name and see the file appear in the directory we wanted. Open the newly created file in a text editor. And see that the molecular orbital occupation numbers are the same all throughout. For the molecular orbital energies, we find non-zero numbers. These energies correspond to the orbital energies before localization, thus, they don't represent anything in the localized version, so we must change them manually to 0 with Excel. Copy and paste the orbital energies in Excel and in a different column, add as many zeros as columns there. Copy them to the original file and save them. If we skip this step, ChargeMol will look for those energies, and since they do not correspond to the localized orbitals, this will produce inaccurate results, unless they are set to zeros. Lastly, move the picture if you saved one to the folder where you are keeping the example. Upon comparing them, it is clear which one corresponds to localized orbitals. Close the multi-WFN window. Open a new multi-WFN window and open the fcheck file in a text editor and again look for density. Now, we find spin SEF as well as SEF density matrix, so we know this example is spin polarized. Load the new example in multi-WFN and view the orbitals. Adjust for optimal view, choose an orbital you want to see represented, and save the picture. Then, choose the orbital localization analysis. Again, the localization method is displayed. Choose to localize only occupied orbitals, 1, and wait for the calculation to finish. Depending on the system, this step may take a while. Then, we choose the Show Molecular Structure and View Orbitals option. We select the same orbital number as last time and save the picture. Now, move both to the examples directory and we see the difference that orbital localization makes. Then, we choose Other Options Part 1. Export various files. Output current wave function as .wfx file. Paste the output path where you want it to be. Open the WFX output file and observe that for charge examples, the net charge is not accurately displayed, so correct the charge and save. Also, we have the same issue with the molecular energies, so change them to 0 using Excel. Now, look that we have molecular orbital spin types, as this example was spin polarized, and we have a matrix for the alpha spins, spin up, and beta spins, spin down. Upon finishing, close multi-WFN. In this example, we only convert the already diagonalized fcheck file to WFX. Open multi-WFN and drag the file to the multi-WFN window. Choose Other Options 100, followed by Export Various Files 2, and Output Current Wave Function as .wfx file. Write the output path and the name of the file. Open the newly created WFX file and fix the charge if necessary. Note that now the orbital energies, which are non-zero, should not be changed to zero if the localization was not done. Close multi-WFN. In example 4, a spin non-polarized coupled cluster calculation is going to be diagonalized and exported as WFX file. Open a new multi-WFN window. Inspect the fcheck file by looking for density. Now we find SCF density and CC density. Drag the fcheck file to multi-WFN. If desired, view and/or save orbital pictures. Remember to change the picture to the directory where you want them. Then choose Other Functions Part 2, 200, and then choose Generate Natural Orbitals based on the density matrix, 16. Then, a secondary menu is going to ask what is the type of density that we have. Choose accordingly. For our case, and as observed the input file, we choose CC. Upon finishing, the program is going to ask if you want to analyze real space functions based on the natural orbitals. Write N to choose No. Now, we want to save the output, so choose Return, 0, followed by Other Functions Part 1. Export various files. Output current wave function as .wfx. Choose the path for the output and add the WFX extension. If you want, you can go back to view the orbitals with the Return 0 option. Open the WFX output and change the net charge to the correct number. Now, we notice that the molecular orbital occupation numbers are not integers, because the orbitals are partially occupied. We also notice that when scrolling down, the number decreases as to approach 0. In this case, we don't have to change the molecular orbital energies as they are already 0. And we see that for this non-spin polarized example, the alpha and beta orbital spins are combined in a single matrix. Close the multi-WFN window. Example 5 shows how to complete a similar process as example 4, but with the spin polarization. Open a new window of multi-WFN. Open the fcheck file and look for density. We now find SCF, spin SCF, and CC matrix densities. Drag the fcheck file to multi-WFN, and if desirable, choose to show the molecular structure 0. Save if you want. Then, go to Other Functions Part 2, 200. Followed by Generate Natural Orbitals based on the density matrix, 16. Choose the input density type, in this case, CC. For this spin polarized case, we get another menu which is asking how we want the result displayed. Option 1 is the addition of spin up plus spin down electron densities, yielding a single density matrix. Option 2 does spin up and spin down separately and yields two density matrices, one for alpha electrons and another for beta electrons. Option 3 calculates the difference spin up minus spin down and yields a single density matrix. Preferably, you will always choose alpha and beta natural orbitals, too. Then choose N, No. Select Return, 0. Following the same path we have done in the past examples to save the output as WFX file. Look how the occupation numbers approach zero scrolling down and then larger numbers as in the beginning appear. This is due to the density matrix being diagonalized by choosing to have alpha and beta densities separated. Also, observe that in the occupations first is the alpha density and then the beta density matrix. Move this saved picture to the working directory. For more videos and tutorials, visit our channel. We thank the NSF Career Award for making this video possible.